Hi everyone and welcome to this new video. We will talk about transient response of first order circuits. In this example we will look at the RL circuit in parallel form, and we have again, like in the previous two examples, a situation with a switching circuit. Now what do we have? We have an independent current source IM and an R as a resistor and inductance L. So these are the values given for the circuit parameters. We have three questions. The first one, A, is determine IL, so the current through the inductor. The second question is calculate the inductor current at a specific time, in this case 3 microseconds. And the third question, the last one, is calculate the time for the inductor current to be 2 milliamps. All right. Now, as in the previous two examples, we have dealt with RC circuits for transient response, and then we have discussed the general form of the formula to determine the voltage across the capacitor. In this case, we have a specific. In another situation, we need to talk about the current. But for the current, it is actually the same situation as for the voltage. So for the current, inductor current, we can repeat the same thing as what we did for the capacitor, but replace everything with a current. So we say the inductor current is equal to the inductor current steady state value plus the inductor current initial value minus the inductor current steady state value times e to the power t divided by tau. So as you can see, again, we have three parameters: the steady state value, initial value, and the time constant tau. Okay, so what is actually the initial condition here, and what is the final condition or the steady state condition, what is the tau, the time constant? Now, before the switch closes, actually the situation for the initial condition, there is no current flow through the inductor. So you can already say initial condition is, let me write it in blue, so for time less than 0, you can already say IL less than 0 or at 0, that doesn't matter, but we sometimes write it like this. So just before 0 is 0 amps. And there is a continuity equation that says the inductor current cannot change instantaneously, so there is some specific time needed for the change. So IL at 0 is also equal to what we have now, and it is actually the 0 amps. Okay, now for the situation when the switch closes, then we have another circuit. The current source and the resistor is connected now to the inductor, and we have a parallel combination. So if this connection is made, and again we wait for a long time, so the steady state situation has created, what we have is the inductor behaves like a short circuit for a very long time. So actually what we get is a circuit like this. So after a long time, we have a circuit which can be modeled like this. And it is the inductor which is short-circuited. And that is actually the current which is flowing through the inductor for steady state. So we can say at steady state, after switching the switch, so closing the switch, then we have the IL for infinity is actually just IM, because all of the current will flow through this wire instead of the resistor. So that will mean the value of the IL infinity is IM, that is 4 milliamps. Okay, so we have two situations for the initial condition and the final condition, the steady state condition. Now, the last one is the time constant. As we said in the previous examples, for the time constant calculation, you look at the situation after the change is made. So the new circuit configuration is when the switch here is closed. So this is actually the new situation, but then of course we look between the terminals of the inductor and we will see what kind of resistance we'll see. There's a Thevenin resistance. So let me write it down again to make the situation clear. So we have a time constant situation. That's our last parameter. Let me draw it again. So we have the resistor, we have the inductor. So we have the inductor, we have the resistor, and what we say is for resistor measurements or resistor calculation, we disable or turn off all independent sources. So for independent current source, that will mean an open circuit. So this will be gone, and we look at between the terminals of the inductor. So we look at like this. This is the Thevenin resistance. For Thevenin resistance, we use in the calculation of the time constant. The calculation for time constants of inductor circuit with the resistor is, the formula is inductance divided by the resistance, not the multiplication. So be careful. And R Thevenin here is very simple R, and that is 1000 ohms. So then we have the tau is equal to 5 millihenries, so 0.005 divided by 10 to the power 3, and that will give us 5 microseconds. Okay, that is actually the last parameter. Now we can fill in this formula, which is given already at the beginning. So we just fill this in, and there's also the initial condition and the final and the time constant, and that will make it up. All right, then IL as a function of time is equal to 0.004, that is the final condition, plus initial condition is 0 minus 0.004 times e to the power minus t divided by 5 times 10 to the minus 6. And if you simplify this, then you will get 0.004 minus 0.004 times e to the power minus 2 times 10 to the power 5 V, and that is actually in amperes. Okay, now that is actually the calculation for part A, so that is done, and you can always simplify this in a further step like this, but that is actually not really necessary. If you want to, you can do it. So this is the final formula. Okay, I will go to the second question. That's actually calculate the current at a specific time. That's 3 microseconds. So I will just fill in this formula, and then we have the situation we want. So IL at 3 times 10 to the power minus 6. So what do we get? 0.004, and then 1 minus e to the power minus 2 times 10 to the power 5 times 3 times 10 to the power minus 6. So if you calculate this, you will get approximately 1.805 milliamps. That's actually question B. As you can see, if you calculate, do a lot of work for question A, then will be the question B and C will be much easier. Okay, Then we have the final question, question C, the third one. The question there is calculate the time for the inductor current to be 2 milliamps. So that's the reverse of the question in B. So actually what we want is we would like to have the inductor current at a specific time, we don't know yet, is 0.002 amps. So the formula is 0.004 times 1 minus e to the power 2 times 10 to the power 5 t is equal to 0.002. So we can use this equation to calculate the time required to get the 2 milliamps. So what I do is I will divide it out, so step by step. So 1 minus e to the power 2 times 10 to the power 5 t is equal to 0.5. I will make a room like this, so I get minus e to the power 2 times 10 to the power 5t, so I will get minus 0.5, and if I divide it by minus 1 or multiply by minus 1, I will get this, and what you get is you use the natural log and you get minus 2 times 10 to the power 5 t is equal to ln of 0.5, and then t is equal to ln of 0.5 divided by minus 2 times 10 to the power 5, and then you get approximately 3.47 microseconds, and that's actually the last question. So that was it for this exercise, for this example. We have a parallel RL circuit having a switch, and we have calculated these three situations for the expression for IL, calculation of the current at a specific time, and also the calculation of the time for value for the inductor current. Of course, we will continue with the new examples, so keep in touch, and I wish you a lot of good luck, and don't forget to subscribe and to like and to share the video. See you next time.